Okay, friends, this is the final talk for the first day of our Geometry Topology Summer School, and Marcos is gonna tell us about left invariant locally conformal Kähler geometry on Lie groups.
Okay, thank you, Mustafa, for the introduction and also for the invitation to participate in this summer school. So these three lectures will be about LCK geometry, which means locally conformally Kähler. I will explain in more details. So what's the plan of this? So I was not completely sure about the audience. So yeah, the first lecture will be really basic. So we will talk about some motivation, definitions about this topic. And the plan for tomorrow is just, I mean, today I will explain this definition at manifold levels. And tomorrow the idea is to convince you that we can do a lot of geometry using Lie groups. So that's I would say, the main aim for me of these lectures. So the idea is just translate the definition we will see today at the Lie group level. And for the last talk, well, we will see some known results about these topics, known results, yeah, open problems, and yeah, we will see. But that will be the main plan for these three talks. Okay, so let me start with some motivation. Can you see there, right? I hope so. Well, if you have any question or something, please interrupt me. I will be happy to answer. So motivation. Yeah, sorry?
It looks perfect, yeah. Go
okay.
ahead.
So motivation. So as you know, in differential geometry, so one of the main, I would say, goals, so is yeah, it's given a manifold, let's say M, try to find nice metric, right? Nice metric G on M, and depending on the setting, on what are you interested in, so there are many definitions for nice metric, right? But at least in Hermitian geometry, so in Hermitian, I will define everything in a moment, so just it's a motivation. So in Hermitian geometry, so one of the nicest metric you can find is the class of Kähler metrics. That's one of the best things you can get, at least in this area, right? But what's the problem? Well, first of all, just some word about Kähler geometry. So Kähler geometry involves, so it is important in complex geometry. We will see more about that. Complex geometry is also related, of course, with Riemannian geometry, because it's symmetric involved here. Riemannian geometry, yeah, symplectic geometry. But one of the problems with this nice metric is that many important manifolds do not need a Kähler metric. So one possible solution for this is just try to enlarge this class, this family of metric, in order to include more examples. So we have the class of Keller manifolds, and we will make this class larger, and this is where the locally conformally Keller manifolds appears, right? So the name is very easy. So it's LCK is for locally conformal, conformal Keller. I will explain in detail the definition of this in a moment. So as I said, this involves mainly three things, at least two. So complex geometry and Riemannian one. So let me start with some definition about complex geometry. Okay. So let's fix some notation. So M will denote manifold, smooth, real manifold. And let me define what an almost complex structure means in a real smooth manifold. So an almost complex structure on M is an endomorphism T from Tm to Tm. So the tangent space such that for each point of your manifold, let's say P, this J sub P is going from TPM to TPM and satisfy that JP square is minus the identity. That's the condition we ask for this endomorphism. And in this case, so we say that M with this almost complex structure is an almost complex manifold. Right? Okay. So that's the first ingredient we need in order to go to define locally conformally Keller. So first Keller and then locally conformally Keller. So what about the examples of this? So as respect, it's very trivial. So Cn is the first example, but here we are talking about real manifolds. So yeah, we identify with R2n. So this is our first example, and the almost complex structure is just multiplication by I, right? So of course we have that this is -1, so satisfy our condition, right? It's minus the identity. So this is the very first example. Some consequences of this space, some consequences, remark, of a manifold admitting this kind of structure, almost complex structure, complex structure. So the first things that the manifold has to satisfy is something related with the dimension. So if M admit one of these almost complex structure, the dimension is even, right? And another consequence is M is oriental. So both things are a consequence of the fact that we can always define a basis in our M with an almost complex structure of this form. So let's say some vectors and then J of them. So here N, so 2M, let's say dimension of M equal to N, right? So we can always find a basis of this form in our manifold. So this is a basis, basis of TPM, right? For every point, you can do that. And any other basis is just conjugated to this basis by a matrix of positive determinant. That's why M has to be orientable. So these are the first two consequences of having this almost complex structure. Okay, so let me explain with more details our first example. So we have R2N. So let's take coordinates, X and Y, 1 until N. So this should be the complex ones, but we want real manifolds. So yeah, we have just the identification of R2N with Cn. This is our local coordinates. Local coordinates. So we need to define a basis of our tangent space, but the basis is the usual you expect. So J is going from 1 to N, dimension to N, and how you define the J? Well, it's just you send the X, the X K to the Y K. This is for any point, right? And since it's got to satisfy that the square is minus the identity, the definition in the other one is just minus the X. Okay, right? So this will be our canonical examples of this. So another example, let's say 1, 2. Point. Another example will be the two-sphere. Two-sphere, we have a point in the sphere, and let's take a vector in the tangent space. So imagine, so we have the sphere, point P, and vectors here, right? So we need to define J, P in this B. How we do that is just by taking the cross product of P and B, right? So you can think about P like a vector here, and then this is B, and JP in B would be this one, right? So it's just something which is orthogonal to P, so it's in the tangent space, but it's also orthogonal to B, right? Okay, so we can check that this is indeed, so JP is an almost complex structure on S2. You can check the square condition. In a very similar way, we can define an almost complex structure on the sixth sphere. So I won't talk about the detail, but the idea is very similar to the previous one, but now we need to use the octonions. So if you use the octonion, take the imaginary part, then take the unitary ones, you can define a sort of cross product there, and there is an almost complex structure coming from the octonions in S6, and with this complex structure, this is almost complex manifold. Okay, so in general, there is a big family of manifold admitting an almost complex structure, and it's the family of complex manifolds. So the next remark is this one. So every complex manifold admits an almost complex structure. So what I mean by complex manifold, so instead of having diffeomorphism with Rn, so here we have local diffeomorphism to Cn, right? So that's the idea, right? So instead of, so you have, let's say U, this is in your manifold, and then you have maps going from U to Cn, right? And the same with another open in your manifold, and this is Cn. And in the intersection, you can define just the composition, and this guy is holomorphic. That's what I mean by complex manifold, right? Okay, so every complex manifold admit one of this structure, and I think you can imagine how we will construct this structure. So the idea is, we know how to do it in Cn, right? So here we have the complex structure of Cn, so it's just the multiplication by I. So we need to define something in our complex manifold, that the J we need to define here. So what? We can use the map P we have, right? So taking just those maps and doing the composition with the J we already have, we can define J in our TPM just by the composition with this canonical J we have. So we are going from this to Cn, then from TPCN to TPCN, and then back. Right, so you can check that this GP satisfy the condition of such that the square is minus the identity. So M complex manifold. So there is a canonical way to induce an almost complex structure. Almost complex structure, right? So the question now is, can we go back? So the question would be, so any, let's say, MJ almost complex manifold is indeed a complex manifold. And the answer is no. So we need some extra condition in order to define a complex, I mean, this local holomorphic map. We need some extra condition. With the existence of this almost complex structure is not enough. And in order to tell you what is this condition, let me define what an integrable almost complex structure means. So an almost complex structure J is called integrable, or sometimes it's also called complex, if this algebraic condition, there is a tensor evaluated in two vectors, Jx. So this is the bracket between Jx and Jy minus Xy minus J of Jxy plus Xjy. Yeah, so this tensor has to be 0 for any X and Y. Yeah. So in this, if this happens, so J is the almost complex structure J is called integral or complex. And we have this result due to Newlander and Nirenberg. That says that MJ, almost complex manifold. Then M is a complex manifold if and only if this guy vanish. It's a very strong theorem, and it's, yeah, for me it's surprising because from one side, so complex manifold, so here we have something related with the geometry of the manifold or the topology, if you want, because it's holomorphic map with Cn, and on the other hand, we have this algebraic condition. So it's just that tensor and J involving the X and Y and the bracket, and has to be 0. So yeah, the theorem is it's very nice. So there is one easy way, which is, of course, if you have a complex manifold, you can define the almost complex structure as we did with this. And from there, it's easy to prove that this tensor vanish. The other way is more. Okay, so we have a lot of examples of almost complex manifold. So, for instance, every complex manifold has one of these J. Good. So, in this situation, when we have this, we will call MJ. It's called the complex manifold. So what it means here, so it means J square is minus the identity. So this is almost complex plus this extra condition, right? So every time we have to check that an almost complex structure is actually complex or determine a complex manifold, we need to check this this condition. Of course, our canonical example Cn real version with the complex structure given by the multiplication of by I is an example of a complex manifold, of course. Manifold. So it means that that's almost complex structure satisfy the extra condition. And one example where the condition is not satisfied is the S6 with the almost complex structure given by the octonions. So in this case, this is almost complex, but the tensor associated with this J is not identically zero, right? So actually, I think it's still open. So there were a lot of discussion about the existences of complex structure in the sixth sphere, right? So you probably heard about that. So here we are only saying that with this almost complex structure, so the condition is not satisfied. So we cannot guarantee that the six is complex, but maybe could exist another almost complex to satisfy. But as far as I know, that problem is still open. Okay. So let me move to the second part. So the first one was about this complex structure. So the second one will be about Keller geometry. Keller manifold, Keller geometry. So if you have any question, please interrupt. Okay, so here was the setting. So we have MG. So M is smooth manifold, G is a Riemannian metric. Riemannian metric. This just means that we have for each point of our manifold, this GP is going from TPM to TPM to R. It's an inner product. And its bar is smoothly from point to point. So that's a Riemannian metric. Now we want to somehow to make a compatibility between the complex structure we already defined and the metric we are talking about. So that's where the Hermitian geometry appears. So definition. So a Riemannian metric G. Riemannian metric G. A complex manifold. M with a complex structure. So here we are assuming not just almost complex, but integrability as well, right? So a Riemannian metric on this complex manifold MJ, it's called Hermitian. If satisfy a compatibility condition with the J. So the metric in JX, JY is the same as the metric in XY for any X and Y. So this is the compatibility condition. Compatibility condition. And in this case, we said that, okay, M with the complex structure and the metric is a Hermitian man. So first observation is that take your favorite complex manifold and we can always define, always exist a Hermitian metric G. So how we define? Okay, let's H, let's say, be any Riemannian metric. On M. With this metric, we can just do the following. So H in XY plus H in JX, JY. And this is the new metric. If we define G as this sum, this G is Hermitian. So we can always construct an Hermitian metric given any complex manifold, right? Okay. So the existence of the metric is not a problem. Oh, sorry. So with this, we can introduce omega. So now we have our three things. So the manifold, the complex structure, and the Hermitian metric. So we are always assuming the compatibility between J and G. So with this ingredient, Hermitian manifold. So with this, we can define the fundamental two form, omega form. How we define omega? It's just a two form, which is is defined by the metric and the complex structure. So that's the definition of the fundamental two form. Okay, and with this, we are ready to say what the Keller manifold is. So this Hermitian. So G, the metric, is called Keller. It's called Keller if this fundamental form is closed. So the omega is 0. Sorry? Is there any question? I think there is some micro open. Okay. If you have a question, please interrupt me. Okay. So this is what a Keller metric is, and in this situation, we will call the MJG just a Keller manifold. Okay, nice. So there is an equivalent, let's say, characterization of Keller manifold. Equivalently, so MJ and the metric G and scalar. If and only if, so the complex structure is parallel where nabla G is the Levi-Civita connection. is the Levi-Civita connection associated to the metric G. So this is another way to say that this Hermitian structure is scalar. But this is the one we will work with. So again, let's talk a bit about some examples. So of course, our canonical example works in this situation. So we have our local coordinates, remember, as a real version of the complex Cn. Local coordinates, then we have the basis of our tangent space. Basis of our tangent space. What's the complex structure here? It's just sending the x to the y's. Sorry, y, k. And the y to minus the x to satisfy the square condition. And what else? And we need to define the metric here. So the metric G is defined such that the basis beta we have is an orthonormal basis. So with these two definitions, we can write down how the fundamental two forms look like. So in this case, it's easy to see that omega is just the sum of txj h d yj. Now we need to sum from 1 to n, right? So this is one form, so this is a two form. This is a sum of n two forms. And of course, if you see how we define each dxj h d yj, it's immediately that omega is closed. So this is the Keller form of R2n. And another less trivial example is given by CPN, the complex projective space, with the Fubini 2D metric. So I won't give the detail of this, but yeah, I can share the detail after the talk with you, or you can Google it. There are a lot of detail about this metric in CPN. Okay, before to move on to the locally conformally definition, let me just give a remark about symplectic stuff. So what we did here, if what's happening, we consider just only omega, I mean, without the Hermitian structure. Without this Hermitian structure, and we ask for this closeness condition, the omega equal to 0. So M manifold with omega and non-degenerate to form it's called symplectic if the omega is equal to 0, and M with this omega is a symplectic manifold. So what I'm trying to say here is that if you forget about the Hermitian structure And the existences of this closed to form give you a symplectic structure in your manifold. So that's why this this scalar geometry involves symplectic geometry, complex geometry, and of course Riemannian geometry, because you have a metric, a complex structure, and this symplectic form omega. Okay, this was just a side remark. Okay, well, let me just go to the main part of the talk for today. So, well, before the definition of locally conformally manifold structures or a manifold, let me just give you a remark about the existences of this complex structure, Hermitian metric, and symplectic structure. So the thing is, any two out of these three guys determine completely the third one. So what I mean by this is, for instance, the Hermitian metric and the complex structure, the Hermitian structure, we already see that we can define omega as we did, right? So that's the easy part. So this is a two form, not degenerate. But if you start with the complex structure and the two form, and of course you ask for some compatibility, condition, which is the condition here is just, okay, omega in jx, jy has to be the same that omega in x and y. So under this condition, we can define G. And how is the definition of G? Well, it's G in xy is just omega in jxy. And similarly, if we start with omega and G, you can induce the complex structure. So here is just, well, you know how omega is, and you have your metric, so it has to be an endomorphism such that realize the two form omega for this given metric, and this is the guy. So you define implicitly J satisfying this condition. So that's the point of the remark. So any two of these three guys determine the third one. So if you want to make a picture of this scalar geometry so far, so for one side we have the Riemannian metric. On the other hand, yeah, you have complex geometry. So for those manifold what mean the compatible structure G and J, so we have the Hermitian first, so J and the metric. So this is Hermitian. And the Keller structure are something in the Hermitian. So it's just the part where so here is Keller. So you need to add to the Hermitian structure. So you know that there exists a two form, the fundamental two form. So when this form is closed, you have Keller, right? But what we want to do now is just to increase this class. So yeah, the picture is not really good. So we need to increase, let me just say here. So we have the Hermitian part, just a sum of this part. So Hermitian, just a little part of this is the Keller. And what we want to do is just to enlarge this class inside the Hermitian class of manifold to include more examples. And here is when the locally conformally Keller appears, right? So that's the picture of this part. So okay, so we are ready to talk about this locally conformally. Conformally or conformal. Okay. I will denote it by LCK. Okay. So I think I will give a definition. Sometimes it's not the standard one, but I think it's clear because of the name. So Hermitian manifold M with our complex and our metric, which are compatible, is called locally conformally Keller if so exists an open cover UI of our manifold M and a family of function Fi from UI to R, mode function, such that each local metric. So we already know that our G, our G is not necessarily Keller, but if we multiply our metric by this factor, so this new metric is Keller on UI. So it's easy to explain maybe. So what the locally conformally Keller means. So for each point in your manifold, you need an open UI so that your point is there and your original metric is not Keller there. But if you multiply your metric by this factor, exponential of minus Fi, so this new metric is Keller. So I think the name is really clear. So locally, your metric is conformal to a Keller one. That's why I like to give this definition, and then we will see a characterization of this, which is much easier to work with. Okay. Perfect. So that's the definition. But of course, if you need to check that a given metric is locally conformally Keller, this definition is, yeah, it's not the right one, because you need to make this open cover, try to find the functions and prove that the local two form associated to this new metric GI is close. But there is this result, which is a characterization of LCK manifolds, and is due to Lee. Was given in 1946, 45, I don't know. Well, around 1945. And it says that MJG is locally conformally Keller. So GJ structure is locally conformally Keller if and only if. So the fundamental form is probably not closed, but has to satisfy this condition. So it's theta wedge omega for some theta one form and close. That's so the omega is a 3 form. Now here we have a 1 form, wedge a 2 form. So yeah, it's a 3 form. So that's the characterization we will use for a locally conformally Keller metric. We talk about locally conformally Keller structure, and normally we say that the metric is locally conformally Keller, or omega is locally conformally Keller. So it's the same, because remember that the metric with the complex structure define the 2 form, and the 2 form with the complex structure define the metric. So everything is the same. And in this case, if this condition is satisfied, in this case, so this 1 form theta is completely defined by this property that d omega is equal to theta wedge omega, and is defined by this formula. So here 2n is the dimension of the manifold. So omega theta is defined by -1 over n minus 1, and this d star is the codifferential operator. Codifferential operator. Omega is the 2 form, and j is the complex structure. So if you have this, if you have a 1 form, closed 1 form satisfying this condition with the fundamental form omega, then this 1 form is completely determined by omega, the metric, and the complex structure. And this is the formula, and it is called the Lie form, or the Lie 1 form. Okay, so this is the definition we will use for locally conformally Keller. It's really useful. So let me just let's say something about the proof of this characterization. So let me go from the original definition of LCK to the existences of this special 1 form satisfying the condition d omega equal to theta wedge omega. Okay, so M, J, and the metric is LCK. And so it means that we have our family of function Fi, and our open cover Ui, these smooth functions, sorry. And we have these local metrics, exponential minus Fi. So metrics defining only in our Ui for each I, and they are Keller. I is Keller for all I. That's the condition. It's Keller, of course, on Ui, right? So it means that we have a local 2 form. So define it just by the local metric and the complex structure. And since this metric Gi is scalar, so what had to happen is this local 2 form is closed. So the omega I has to be 0. That's the condition we have just from the definition of locally conformally Keller. But if you take, so let me just, okay, let me first, before doing the derivative, let me first write down exactly how these 2 forms look like. So this is exponential of minus f and the original metric, right? But this is the definition of the fundamental two form associated with the metric G. So this is x minus f omega in x, y, right? So what we have is, yes, this omega y is just this multiple of the original omega, but of course, this is just on UI. And as I said, the local metric is scalar, means that this two form is 0, but we can compute the derivative of this omega I. It's just the derivative of the first part, h omega, and the first part, d omega, right? Well, if we do the computation, so it's minus dfi, exponential of minus f, and d omega, plus this guy. And we can take the exponential as a factor. And here we have minus dfi. Sorry, this is omega. Omega plus d omega. And since this guy has to be 0, so we have that d omega is exactly dfi h omega, right? So here we can already see who is our candidate for the Lie form, right? So should be this dfi. But what's the problem? This is a local definition of theta, right? So we need to check that. So this is just on UI. So we need to check that this guy is well defined in the intersection of two. So what's happening? We have UI, UJ. So what's happened there? So from one side, we have that dfi, which omega is just the omega. And from the other side, from the J side, this is dfj, which omega, right? Okay. So if we take everything from one side, what we have is this guy has to be 0. This is on UI intersection UJ, right? But since omega is non-degenerate, the only possibility for this wedge being 0 is just dfi minus dfj has to be 0. So that's it's a proof that this local dfi define a one form we call theta globally. So it's well defined, and on each UI, this theta is dfi. And of course, the theta will be 0, right? So we prove that d omega is theta h omega for this closed one form. Sorry. So from the definition to the existences of this one form satisfying this condition, we are done. And to prove the other direction, so this is very short. So if you already have this condition for one form, closed one form, and omega, of course, the fundamental form, what we can see is that by Poincaré lemma, so theta has to be locally exact. So theta has to be d of fi for some function. So exists an open cover ui, and these functions by the Poincaré lemma, smooth functions, such that theta is the fi on ui, right? And if you go back from this equation, it's easy to see that that this fi satisfying the condition in the definition. So what we have so far is this, right? So the omega was theta wedge omega. So on each ui, this is just dfi wedge omega on ui, and we need to show. So what's the condition in the definition? We need to show that our local metric, so exponential of fi times the original metric, so this is, remember, this is gi, has to be Keller. That was the definition said about locally conformally Keller. Okay, how we prove this? Well, this is equivalent to say that the local fundamental two form associated with this gi, with the metric gi, the local two form defined by the gi has to be Keller, has to be closed. Has to be closed or has to satisfy has to be closed. And we will see this, but it's almost immediately from the condition we already have. So d omega I is just x of minus fi. I mean, we can check, but it's the same computation we did before. And with this, we have this. But remember, this guy was the local definition of our one form theta. So this is just minus theta plus d omega, right? But that's the condition we start with. So this is 0. So d omega I is 0. So omega I is closed and gi is scalar. That how we show that if you start with the condition d omega equal to theta wedge omega, you can construct this open cover and these functions and prove that locally your metric is scalar up to this conformal change. Okay, so from now on, so omega will be LCK, so locally conformally Keller, omega or the metric or the Hermitian structure. I mean, I'm omitting the detail, but yeah, you can say omega or just GJ. But what we means with by locally conformally Keller is just this condition is satisfied for a closed one form theta. So this is the best characterization to work with. Okay, let me comment some fact about this locally conformally Keller metrics. So remark. So the first things I want to say is that this condition is conformally invariant. So what means that if you start with some omega 0, which is LCK, and you define a new one, just as the original one by multiplying by some factor exponential, let's say minus f. So the minus is just to get better computations. So this is also LCK. And it's very easy to prove. So if you take the derivative of this omega 1, this is just the exponential of minus f df. Well, sorry, here is not necessarily the minus, I guess. Yeah, it's the same. Which omega 0 plus the omega 0. But omega 0 was LCK. So this is just theta 0, which omega 0. So what we have here is exponential of f df omega 0 and theta 0 h omega 0. So we can put everything omega 0 at the end and have just this df from the first part and theta 0 from the second one, which ef exponential of f times omega 0, right? But who is exponential of f omega 0? So this is the new omega 1, right? So what we have here is just a one form, df plus theta 0, which omega 1. So the omega 1 is just a multiple of this omega 1 again, and this guy is the one form, and of course it's closed because, yeah, it's the only difference with theta 0 is just an exact form. So this is closed, and this is theta 1. So as you see, if you change a little bit your omega 0 by this factor, so you obtain again a locally conformally Keller structure, and the one form theta, the Lie form, is very similar to the original one. So the only difference is this exact part. So it's conformally invariant. And this class of locally conformally Keller generalize the Keller one. So of course, when the Lie form is 0, so we have the condition the omega equal to 0, so Keller. So it's really a generalization of the Keller geometry. Some other interesting facts. Well, yes. So if theta is exact, I mean globally, we already know that locally is exact, but globally exact. So this it's called globally conformally Keller. So globally conformal Keller. So what means that, yeah, your original omega was not Keller, but if you change it by this exponential of minus f, where the f is theta, so this is Keller. So somehow we want to avoid this situation, and we are interested in LCK, let's say strict, which means not globally conformally Keller, right? Because if you already have a metric with this globally conformally Keller, okay, up to this conformal change, you already have a Keller metric. So work with that one, which is much better than any other. So that's why we are interested in locally conformally Keller metric, which are not globally Keller, right? Okay, that's all I want to say about this fact as consequence of the definition. So maybe let me just try to finish with an example. Okay, so non-trivial example. So Hopf manifolds. So what a Hopf manifold is, so it's just Cn minus the origin. And there is a relation that Z and lambda Z, we identified Z with lambda Z. So with lambda is a complex number and modulo is different from 0 and 1. So as a manifold, so this is just S1 times S2n minus 1. And you can see, you can compute the first Betti number of this M, and this is 1. So it means that M doesn't admit any Keller metric. So will be an example of a really strict LCK, any Keller metric. So why is that? Is because compact Keller manifold has a property that the odd Betti number has to be even, right? So in this situation, it's impossible to have a Keller metric. So as a manifold is this, but we want to construct this locally conformally Keller metric. So what's the idea? I will try to do the computation on Cn minus the origin, and we will define the metric, the complex structure, and the fundamental form there. And we will see that this structure descends to the quotient and will induce an LCK structure in the quotient, on the quotient. Okay, so let me start with the local coordinates. So complex one, local coordinates. So we will start with the metric H, which is just the set J and the set bar J. So the complex conjugation, and we need to move out by the modulus of Z. So again, the dimension of the manifold is 2n here. So this is a metric on Cn minus 0. We will define complex structure J. Well, here is the canonical one. We have Cn minus the origin, so it's the canonical structure. So it means multiplication by, so GB is just, yeah, it's multiplication by I. Okay, nice. So, but this is not the metric we want. So what we will have is just take the real part of this metric H. So G, our metric will be just the real part of H. And you can make the computation, but I will just say that this is dxj square plus dyj square. And again, we need to divide by this. So this metric is compatible with the complex structure. So we have a Hermitian structure. But again, this is just on Cn minus the origin, right? But if we pay attention to this, so I think it's clear that so the metric G in any point Z, I mean X plus IY, So it's exactly the same that G in lambda set, right? Because from the top part, from here, so there is a lambda square as a factor, and the same in the denominator, so will be cancelled. So the metric in set and lambda set is exactly the same. So what I'm trying to say is that this metric, and indeed the Hermitian structure, descend to the quotient, to M, descend to M. So we have a, let me write down better here. So G, J on Cn minus the origin, descend to M. And we will call it, I don't know, I can call it just GJ, sorry, GJ, G tilde, J tilde. So that's the induced Hermitian structure on M, on the quotient. And with the metric and the complex structure, we can define our fundamental two form, omega. The definition of omega, well, you already know it's just this one, right? And you can check that indeed omega is dxj, which dyj. And here we need to sum by the square of x plus y. So that's the definition of the fundamental two form, again, on Cn, right? But of course, again, you can use a lambda square factor. So omega in Z is exactly the same that in lambda Z. So again, this induce an omega tilde on M. So we have the induced fundamental two form in the quotient, right? So we need to check to finish just that the condition of locally conformally Keller is satisfied. We will prove it on Cn minus the origin because everything is the same in the quotient, just with the induced structures. So let me just call f to this 1 over, so the denominator part of omega. So it's 1 and the sum of this guy. So with this new notation, omega is just f times the sum of this. Right? Okay, perfect. And to compute the derivative of omega, we will see df. So you can really do the computation, but yeah, this is just, so we need to compute partial derivatives of f, the direction of x, plus the other ones in the direction of y. For any k from 1 to n, and you can really do this computation, and it's turn out that this is minus 2f squared, and the sum of x dx plus y dy. And with this, we can really check that d omega is minus 2f squared and the sum of this guy. So I'm just doing the computation of d omega. Which dx dj, but this is exactly, so if we split f squared and we put one f in this side and one f in the other, So this is minus 2f. And here is the sum of the things. And if the other f is going to the last part, this is exactly the definition of omega. So we have this, right? Okay, so this let us know that this part is the one form we need. So if we define theta just by this, so we have that the omega is theta wage omega. And if you see how this theta is defined, it's very easy to check that this is close, right? You can do it as an exercise. And again, the definition of this theta descend, because it's f times something, descend to the quotient. So the lambda, it's canceled if you do it in lambda set. And we have that this omega theta LCK on Cn descend to an LCK structure that's called tilde in the quotient, on the quotient. Which is called N, right? So that's the structure, the locally conformally clear structure on our manifold M. And so this is just the last part. So if we pay attention, so this theta satisfy an extra property. So it's not just LCK, but theta tilde has an extra property, which is that it's parallel with respect with the Levi-Civita connection associated with the metric we have. And this is actually a well-known subclass of locally conformally Keller. So let me just finish with this definition and we will continue tomorrow. So there is a special subfamily of LCK. So M, J, and the metric G, LCK, it's called Weismann structure or Weismann manifold. It's called Weismann if it is LCK and the Lie form is parallel with respect with the Levi-Civita connection associated to the metric G we have. And indeed, this Weismann manifold are always LCK strict. So the first, you can prove that the first Betty number of a compact Weismann manifold is 1. So it's never admit a Keller metric. And yeah, there are a lot of results related with this Weismann manifold, which is a particular subfamily of the locally conformally Keller. And we will continue with this, yeah, probably tomorrow. So I think I will stop here with this general definition. And yeah, thank you.
Okay, thank you very much. Thanks for detailed proofs and examples. Great.
Okay.
Any questions? All right, thank you very much. And we're going to meet tomorrow morning at the same time.